Hello, and thanks for coming to our talk. This is work with Elizabeth Simmons. We're talking about interactions of length and overlap in the trace model of spoken word recognition. Our focus is on similarity and competition, that is similarity mapping for mapping the speech signal onto words in memory. This seems like a simple question, but the answer will reveal fundamental details of human speech recognition. To get us oriented, let's consider two foundational proposals for rule-based principles that might define the set of items that are activated during that process. The cohort model focuses on word onsets. And we say onset primacy because the way that it operates is as input is coming in, it is mapped phoneme by phoneme onto words in the lexicon. As long as words continue to match the sequence so far, their activation increases. As soon as they mismatch, they are deactivated and removed from the recognition cohort as quickly as possible. So that means that words like cat will activate competitors like can and castle, but not words that mismatch early on like bat. On the neighborhood activation model, the sequential nature of speech is set aside and the focus is on global similarity, and the proposal is that two words will be neighbors, and therefore when one is heard, it will activate the other if they differ by no more than one phoneme. So this means that for a word like cat, can will still be a competitor, castle will not because it differs by too many phonemes, and a word like bat would be predicted to be a competitor because it only differs by one phoneme. Okay. Now, an alternative way to think about similarity mapping comes from the trace model of spoken word recognition. Trace is an interactive activation neural network model where we have pseudospectral features that feed up to phonemes that contain them, phonemes feed to words that contain them, words send feedback to their constituent phonemes, and there's lateral inhibition between word nodes and between phoneme nodes. So we have a bunch of simple elements that follow extremely simple rules, but when you put them all together, very complex behavior emerges. And Trace does a surprisingly good job of simulating various aspects of human spoken word recognition, including the fine-grained details of phonetic competition over time. So here we have some data from Alapena, Magnuson, and Tannenhouse in 1998. Participants saw displays like this and heard an instruction like pick up the beaker. And critical displays included competitors like beetle and speaker, potential competitors of beaker, as well as an unrelated baseline like carriage. And what we found was that starting from the onset of the critical words, such as beaker, we observed what looked like strong early competition between items overlapping at onset, beaker and beetle, and later weaker competition with rhymes, right? So in this case, speaker is a rhyme of beaker. Okay. Well, Trace turns out to predict this pattern quite readily. If you're familiar with this area, this particular trace activation plot is a little different from what you might be used to. We're looking at the mean activation over time of potential targets, cohorts, rhymes, and unrelated baseline items for every possible pair in the trace lexicon. And you can transform these activation patterns with a single parameter into something that would be much closer to fixation proportions. But what we see is the correct relative pattern, right? Early strong competition with cohorts, later weaker competition with rhymes. So we can see principles begin to emerge in the patterns of behavior within the model, but then we still have to figure out where those come from. But because it's an implemented model, we can actually inspect its inner workings and get some ideas for mechanisms that might be operational in human spoken word recognition. Our motivation for the current study came from an experiment Liz did where she's downward extending the visual world paradigm for young kids. And so she's just using two items on the screen at a time. And this is data with adults, just doing some proof of concept, and she discovered something interesting, which is an interaction with number of syllables and degree of competition effects. So for monosyllabic words over here, what we see is we have mean fixation proportion to targets and distractors over time from the onset of the target. And in black, we're showing the fixation proportions to the target when it's displayed with an unrelated item, in blue when it's displayed with a rhyme, and in red when it's displayed with a cohort. And then we have the corresponding competitor or distractor fixation proportions over here. And what we see is a huge cohort competition effect for monosyllabic words and a small but significant one for rhymes. When we move to bisyllabic words, the cohort effect is still there, but it's substantially smaller, whereas the rhyme effect has gotten substantially stronger. To try to get a sense of why this might be the case, we did simulations with Trace. So we added items to the lexicon so we'd have well-balanced sets of cohorts and rhymes. And we use the conventional definition of cohort, where cohorts overlap in the first two phonemes. So we've got bot, bos, and we've got kazdit, kaprad, okay? And then our rhymes always differ only in the first phoneme, right? So now we have short and long rhymes. And so what we see over here is we've got short cohorts and rhymes on top, long on the bottom, and for cohorts we see stronger competition than for long cohorts. So to unpack this, what we're showing in these plots is in black we have the target, in red we have the competitor, in blue we have an unrelated baseline, and then the purple open symbols are the competitor minus the unrelated baseline. So that shows us how much competition there is. And we see a higher peak for short cohorts than long cohorts, but the opposite for rhymes. It's relatively subtle, but we get a higher peak for long rhymes than for short rhymes, consistent with what we saw with the human data. However, there's an alternative explanation here, which is that as we increase word length, the rhymes actually have a higher proportion of overlap with each other than the cohorts do, since the amount of overlap was fixed at just 2 phonemes for the cohorts. McQueen and Viebahn in 2007 proposed the proportion of overlap could actually be a sort of an overarching principle that explains differences in amount of competition. So rather than only having cohorts match in the first 2 phonemes, they created what we call maximal cohorts with high proportion of overlap or low. For high, they're these long words that overlap in all phonemes except for the final one. So they have more overlap than typical cohorts do. The general result, and they did the same with rhymes, and the general result is greater competition in the visual world paradigm for higher proportion of overlap, which suggests that listeners must somehow normalize the weight of a mismatch relative to word length, right? So they must somehow normalize by word length. Well, McQueen and Viebahn proposed that, but they didn't actually suggest a mechanism, so that's an interesting question. And also, it's fair to note that in their items, proportion of overlap is actually correlated with length, and that means it's also correlated with simply total overlap, which could be a different explanation for their results. So our first step was to try to simulate their results. So we have the same items that we had before for the Simmons and Magnuson simulations, but we've replaced the long cohorts so that now they're maximal cohorts. Instead of just overlapping in the first 2 phonemes, they overlap everywhere except for the very final phoneme. And now this changes things. So the rhyme effect is the same because it's the same items. So we have stronger competition for long rhyme items than short rhyme items. But now that's also true for cohorts. We get stronger competition for long cohorts than short. Okay. But again, this is with maximal cohorts, and proportion of overlap is correlated with total overlap. So we set out to do a new simulation where we would dissociate those 2 things and generate predictions for experiments with human subjects. So now we have cohorts and rhymes that are short or long and that have either 67% or 75% overlap. So for the short items, these are actually pretty consistent with the kinds of items we would typically use, right? So keep and keep overlap in the first 2 phonemes, but the 75% actually overlap in 3, so that's a little more than usual. For rhymes, they mismatch in the first phoneme for both the 67% and the 75%. But then for the long items, we have to do something a bit different. And we deviate from the standard rhyme definition that we use in this literature, which isn't poetic rhyme, it's not phonological rhyme, it's actually overlap from the first phoneme onward. Sorry, first vowel onward. So instead what we have is for 67%, we have the first 2 phonemes being different. So what we wind up with is overlap in 4 out of 6 phonemes. And for 75%, again, the first 2 mismatch, so we wind up with 6 out of 8 phonemes overlapping. Okay. So what do we see when we apply trace to these kinds of items? Well, let's look at cohorts first. And what we see is that we get greater competition for 75% overlap than 67%, both for short cohorts and for long cohorts. Okay, so it looks like proportion of overlap is doing something interesting here, except we also see a difference just for length, right? So there is more competition for longer, 67%, and for longer, 75%. Okay. Furthermore, it's not the case that the words that have highest overlap compete the most, because in fact, the long words with 67% overlap have more competition than those that are short with 75%. And in fact, it looks like total overlap is really the most general principle we can appeal to here. Because when we have overlap in 2 phonemes, Here's the amount of competition. Now we have overlap in 3, 4, 6, right? It just steps up with the number of overlapping phonemes. For rhymes, it's a bit different. Just to summarize where we are so far. Okay, so for rhymes, what we see is an increase in competition when we go from 67% to 75% overlap. However, remember, now our long rhymes actually have 2 mismatches. We actually see less competition for long rhymes than short rhymes. But again, they're not really true rhymes, so that's not surprising. But it is a very specific prediction made by the model. Okay, so it seems that proportion of overlap is not a general principle to appeal to. Total overlap is more on track. So where does this interaction arise in trace? Well, it comes from length and some complex dynamics. So before, when I showed you a caricature of the model, right, it was this cartoon, but in fact within the model there's a lot of complex structure. So within the phoneme level and within the word level, we actually have many copies of every phoneme and every word, and they're tiled sort of in this way that converts space to time in trace's memory. And they actually align with specific points where sensory input can impinge on them. Okay, so if we have phonetic features that correspond to ka, and ta, which we're just sketching in here as just they're present, what's going to happen as the input comes along, those features are going to activate phonemes that are aligned with them in time. Those phonemes are going to activate words that are aligned with them in time, depending on their similarity. Okay, so the darker a tile is shaded here, the more activated it would become given this input. And so we see this one copy of cat is going to be very strongly activated, but we're also going to get strong competition from other copies of cat and also words like cohorts like castle. All right. But now some additional things come into play. So let's look at that maximally activated copy of cat. Inhibition matters as well. The thing about trace is words have a width that corresponds to their width in phonemes, and they can only receive inhibition from words that overlap with them in this sort of space-time in the trace model. So cat gets activation just from words within that shaded band, whereas that most activated copy of castle gets a lot more inhibition because it's wider and therefore it receives more inhibition. So this leads to some interesting effects of length in trace due to that inhibition dynamic. So on the left we have a trace simulation where artist is the input, and on the right where art is the input. And what we see is an early short word advantage where words like are and art activate more quickly than a word like artist. And the reason is, even early on, just tiny bits of inhibition coming to artist because of its wider extent is enough to slow down its activation, enough to allow those shorter items an advantage. But later on that turns into a late long word advantage where long words achieve higher overall activation due to greater bottom-up input. So this leads to a discussion of how trace accounts for these diverse previous results we've discussed. So Simmons and Magnuson, right? So for conventional cohorts that overlap in the first 2 phonemes, we see stronger competition for short pairs than long pairs because of the early short word advantage. Rather than something like explicit length normalization, short words have fewer inhibition sites, which allows them to activate more quickly. Long rhymes show greater competition than short rhymes just because of total overlap. That accumulating similarity allows the longer rhyme to overcome more of the inhibition that it receives from the target and its cohorts. For the McQueen and Viebahn simulations with maximal cohorts that overlap all the way up to the final phoneme, the same principle applies, where total overlap, not proportion of overlap, accounts for greater activation for longer pairs. And then we also show these new predictions when proportion of overlap and length are crossed. So in conclusion, general principles like proportion of overlap are attractive, but they have to be linked to mechanisms. And when we attempt to do that, we discover sometimes that those principles don't extend as generally as we hoped. So in trace, the interactions of length and overlap emerge from complex dynamics which allow trace to simulate seemingly divergent results. And trace also makes these interesting novel predictions for interaction of length and overlap when these factors are dissociated and crossed, potentially elucidating some new mechanistic principles, but so far only in trace, and an experiment with human subjects will have to wait until we can resume in-person data collection. So with that, thank you very much.